Okay, good morning, everyone, and good evening for those in the Middle East and South Asia. And thanks for joining for the third and last day of the Sensing River workshop. So today, as you can see, the agenda, we will have the first session is on remote sensing of river temperature. And Shahryar Ahmad will be presenting his research on how to use satellite remote sensing to estimate the stream temperature and how this can impact the operation of reservoirs. He will show us his case study in the US. And then we'll have a break for 15 minutes. Then the second presentation. I'll be presenting on the system that I just introduced yesterday on the Nile Basin Reservoir Advisory System. Then we'll have a break for 15 minutes. And the final session today is to conclude for this workshop, and we'll have a kind of open discussion, and we'll see how we will handle this discussion. So thanks again for joining for the second day. And yeah, I just sent an email like 1 hour ago, I think, for just a kind of some updates. I shared with you in the Google Drive an example for how to drive the area elevation curve using ArcGIS as well. And it's actually an example from a remote sensing class that I have taken here at the University of Washington. Because when I first came here, they were not using they didn't use the Google Earth Engine, and they were still using the ArcGIS. But now they shifted to the Google Earth Engine. So I wanted to just share this so you can have an idea if you want to compare the steps when using ArcGIS and also using Google Earth Engine. So I think it would be good if you want to go through this example. It's for one reservoir, I think, in Mekong River in Southeast Asia, and you will see the Landsat images downloaded already. But you have to imagine if you want to download the Landsat image or to get the satellite images. So this also takes some time. But anyway, the example is there if you want to explore it later and see, compare it with the steps of the Google Earth Engine. That would be good. I also shared the slides from yesterday for my presentation and Indira as well. And again, for my slides, I apologize that I cut some of the slides for the results of the second part of my presentation on the highest one dam operation under the different scenarios of the GERD. And it's just because that it's currently this work is under revision in one of the journals. So I just I'm just waiting for the journal. If it gets accepted, I promise that I will be sharing this paper with you all. And then the last thing is that also I provided you with all the scripts of Google Earth Engine. So I give you all the links. But just make sure when you go to the link of an exercise, try to save this link into your Google Earth Engine folder. So you make sure that you have this script for yourself. So you can use it in the future, you can change it, and feel free if you have any questions, or sometimes you find some errors and maybe you're getting any error. So feel free to contact me and we try to fix this. So I think that's everything I have to say for now. I will stop sharing, and then Shahryar, you can start sharing your screen. And I think while Shahryar starts sharing his screen, I will start. I think, Shahryar, are you able to share your screen? Okay, so let me introduce Shahryar. Shahryar actually is a research assistant here in the Department of Civil Environmental Engineering at University of Washington in Seattle. And he's doing a great research here. And his interest actually in the intersection of water and energy nexus with finding more opportunities to produce energy from water, or probably, the hydropower production. So he's trying to maximize the operation of reservoirs to produce more hydropower. So in his research, he has used a lot of land surface modeling, machine learning, numerical weather prediction modeling, geospatial data processing, and he has done a lot of research using these different tools. Also, one thing about Shahryar, he has done an internship working for NASA Space Flight Center, or the Goddard Space Flight Center in 2017, helping them in the land information system software framework. So he has actually done that with Nishan as well. So I just forget to mention that for Nishan, but both of them, Shahryar and Nishan, they have done, they have helped NASA for the development of the land information system. Shahryar also has received many awards. He's received an Academic Excellence Award from in India, and also here in Washington, he has received the Washington State American Water Resources Association Student Fellowship. So please join me in welcoming Shahryar Ahmad, and let's enjoy his talk on the using satellite remote sensing in river to estimate the river temperature. Shahryar, it's yeah, the mic is yours.
Okay. Thanks, Hisham, for the introduction. All right. Hello, everyone. Good morning and good evening to all of you. So I hope you have been enjoying this this workshop over the last 2 days, and we'll be hearing more today. We have 2 sessions, and hopefully we'll learn something useful from this talk. So I'll be talking today about this topic on remote sensing of river temperature. And this has been quite important in the recent times when we consider how we are affecting our ecosystem and the environment, our aquatic system like fisheries and different kind of species that we have, and so they all depend a lot on the water quality, and river temperature is one of the main factors that drives the water quality. So we'll be looking at it from the point of view of remote sensing and how we can monitor it. All right, so let's begin. So here's a brief outline. So first, I'll talk about why do we care about water temperatures to start with, and why are they important for our habitat and our environment. We will then look at different techniques of measuring river temperature. How has it been done conventionally, and then how remote sensing has been changing the state of the art in the recent times. And then we'll look at why do we need remote sensing and how it works. Finally, we'll end with a small application on the impact of dams, and we'll look at it, how dams are affecting the river temperature and how can we monitor that. All right, so and also just feel free to stop me anytime, and if you have any questions, or you can just type in the chat box or wait till the end. So, so why do we care about river temperature? So if you see this small kind of Venn diagram, so this temperature actually controls a wide number of water quality parameters. So if you might be aware of some of them, for example, dissolved oxygen, we have salinity of the water, conductivity, we have acidity, and different multiple parameters. And so all of them actually are primarily controlled by the water temperature, and any fluctuation in the water temperature can actually cause changes in these parameters, and then the organisms that depend on these water quality parameters, they also get affected. So just to give a bit more detail on how these affects, for example, like on the top left, you see oxygen content. So we have, as water temperatures get warmer, the amount of oxygen that it can contain gets lower. So if there are some organisms that, for example, need higher oxygen content, and then suddenly all of a sudden we have a warmer temperature as compared to what it has been in the past few decades, that might be causing harm to those organisms in terms of their metabolism and then their growth and survival. Similarly, we have other parameters like photosynthesis rate. It is very important for some of these plants and these species that's drawn here. Similarly, we have acidity of the water that also increases as the temperature increases, right? So any small fluctuation is enough to change these parameters substantially, and then that can cause major harm to the organisms. So just an example, so one of the very serious outcomes that is very disastrous and can cause a lot of harm is to the fishes. So there's a fish kill from rapid temperature fluctuation. I think this is on one of the coasts in Florida or something. And so this actually causes, this is actually the aquatic organisms are very, very critical in terms of what is the water quality. And then all of that is controlled by this water temperature. So this is one of the reasons why we should study water temperature and how to measure that. So what controls the river temperature, right? So obviously, first of them is our ambient surroundings. How much is the sunlight? Is it sunny? Is it air temperature warm or cold? That will obviously guide the how much water temperature is there. Then we have hydrology, for example, lakes as compared to reservoirs, because rivers as compared to reservoirs. So because rivers are flowing very fast, so they might be not that so they will not be in contact with the warmer temperatures for that longer time as compared to reservoirs. I will come later in a bit more detail on how reservoirs work, but then there's a difference between how the lakes behave versus how the rivers behave, right? And so hydrology controls a lot the river temperatures or the temperature of the water. Similarly, then we have another factors like turbidity. For example, a turbid water will be absorbing more sunlight, and then it will get heated higher as compared to a fresh water. Then, as I mentioned before, air temperature. So people have developed relationships on how air temperatures relate to this water temperature, right? So for the most part, it is linear. So if you have higher in the summers, for example, water temperature is obviously warmer as compared to the air temperature. But then, and then if you go below zero, obviously it turns into ice, and then there are some modifications in how it relates to the air temperature. Finally, we have a very, very important factor that controls the river temperature is the human impacts, right? How we are changing the environment, how we are building more and more, and how we have like polluting more and more, that is causing feedback on the water temperatures. Similarly, we have dams that have over the past like 15, 20 years, they have caused major changes to this thermal regime of the upstream and downstream rivers, right? So we have so when a dam is built, so that divides the natural river into upstream part and the downstream part, and so that is very, very prone to susceptible to causing changes in how the upstream temperature behaves as compared to how the downstream temperature works. So now we know that we have these changes in temperature, and this is very important, and what factors control the river temperature. Now let's look at how has it been over the past, right? So one of the key complications that occur in measuring water surface temperature or river temperature, for example, is the excessive seasonal fluctuations. So, for example, obviously in the summers, when the air temperatures are warmer, we have the river temperatures are in contact with the air temperature that are warmer, and that leads to a warmer river temperature as well. Compare that to the December or in early spring and in winters when it gets cooler and the river temperatures are cool as well, right? So this is just one snapshot of all the major stations in the US that are measured by one of the agencies here in US called USGS. It is United States Geological Survey. So that has like a very good network of in-situ data collection. It monitors a wide number of variables, for example, discharge. It measures the river temperature. It measures air temperature as well, and it has multiple variables that it monitors. So this data is from USGS, and then it monitors here the stream temperature at each of these locations that you see, and you can see how it varies over the year. So this is one of the complications that occur when we try to monitor river temperature. All right, so let's look at how have we been monitoring water temperatures over the past. So the conventional method is obviously we have been using stream gauges. So we can attach. So obviously we try to measure the discharge or height of the river, for example. But with that, usually they try to install thermometers or data loggers that have these sensors that can sense the water temperature. Right. So now you should notice that the temperatures that are monitored by these stream gauges are actually, so these gauges are in contact with the water, right? So they measure the kind of bulk temperature of the water surface. This will this information will be useful when we compare later to how remote sensing monitors. And so just keep that in mind. So yeah, that's as I mentioned, the kinetic temperature is just the temperature of the bulk of the water. Like if you put a thermometer inside a glass of water, the temperature that it measures, that is called kinetic temperature. But it has obviously some of the disadvantages that demand improvements in how we monitor. For example, it is sparsely sampled. We cannot put like millions of gauges all over the entire river, right? So obviously there are limitations, logistical limitations. Then we have, usually these are located in larger rivers because there are limitations to how much we can put. So we try to put in the locations that are hydrologically useful, or from the point of view of ecosystem and biodiversity, we put in only in those locations. And it is difficult to collect this spatially extensive data, right? We cannot put gauges all over the rivers as mentioned. And also we need calibration of these thermometers because depending on what kind of environment it is located in, or the properties of water, for example, a turbid water as compared to a fresh water, we need to calibrate as well. So it requires a lot of manual work, and it is complicated in that sense. And further, just to add to that, right now we have a very poor network of gauges in many countries. In US, it has a good network that USGS has been monitoring over many decades now. But then, even then, if you compare the number of observations taken by USGS of temperature as compared to, for example, stream discharge or something, it is like around 7% or so. Only 7% of USGS gauges only monitor the temperatures, right? So there's limitations with that as well. All right, so let's move to the what is of interest to us right now. So, thermal infrared remote sensing has been emerging in the past like 2 decades, since like Landsat started, and it has this thermal sensor. So that's when it started picking up, and now many applications are coming where they are using the thermal infrared remote sensing. So how it works, so it will go into more detail in a few more slides, but to give an overview here, it measures the radiant temperature at the water surface. What I mean by that is, the amount, so when the light gets reflected from the surface of water back to the satellite, so that is reflected only the topmost portion, around 100 micrometers of layer of the water surface is actually contributing to the reflection, right? It doesn't matter what are the properties of the deeper waters, right? Only the surface is contributing to the reflection that gets back to the satellite sensor, and then that it measures the water temperature. So now there's a contrast. So the USGS gauges or the in situ gauges or thermometers, they monitor but they are actually in contact with the water as compared to how remote sensing measures. So I'll mention here some of the pros and cons of remote sensing. Obviously, remote sensing, it gives a bird's eye view. So it can be spatially extensive. We can monitor the entire rivers or larger, like it is actually globally scaled Landsat data. So you can monitor almost anything. And then it is a repeat monitoring at fixed intervals. For example, every satellite has a repeat interval. For example, Landsat goes bi-weekly, as you know by now. So we can actually do some change detections. How has the temperature been changing over the different days, because we get this repeat monitoring of these river temperatures. What I mean by here, the last point, non-absolute temperature applications, because we still need some kind of calibration, because it is not giving us the bulk temperature as given by thermometer. So that remote sensing has been quite useful for applications where we don't need the absolute temperature of water, right? Even if we know the fluctuations, like how it changed from yesterday, it changed by 2 degrees, right? So that should be enough for us for some applications, just to know the fluctuations. So in those cases, specifically, remote sensing can come useful. So you can think of some applications that you might be interested in, and that require non-absolute temperature applications, and remote sensing can come handy for that. There are some also disadvantages. As you know, Landsat is one of the optical sensors. It is obstructed by the cloud, so that always is a problem. And then we need some correction that I will talk about later also. And then it is not representative of the bulk temperature, right? So we cannot do an absolute temperature, but although we can do some bias adjustments using other data sets, and then we can improve the quality. All right, so a couple of slides from here, I will show some of the workings of how thermal infrared remote sensing works. If you have taken a basic course, you might already be aware of it, but it is good to revise anyways. So, so you all know this diagram of the electromagnetic spectrum. We have starting from the lowest wavelengths, going to all the way to the microwaves that are highest wavelengths. And so this part actually is the infrared part, starting from 0.7 microns to 12 or 14 microns, right? And so this part is called thermal infrared, right? So there are two parts of infrared: reflective and thermal. Thermal is actually, that is where the most part of the Earth actually reflects in the infrared region. And so this has been useful to us. And then actually in this region also, there's the obstruction from the reflections from other sources actually gets minimized. I'll talk more about what I mean by that. And so actually all materials above 0 Kelvin continuously emit these radiations in different bands depending on their temperature, right? And so there's a law called Wien's displacement law that says that as the object gets hotter, it emits the wavelength of a shorter wavelength radiation, right? So if I have two objects, one is at a higher temperature, other is at a lower temperature, so the higher one will emit in the higher shorter wavelength. So it is an inverse relation. So just to give an example, where do these radiations occur based on the temperature? So there's a very famous law called Planck's law. That it's a very, like, in a very simple terms, it says that any body emits radiation that is dependent on two factors primarily. One is the wavelength, like what kind of wavelength it is emitting, and then other is the temperature of the body, right? So if we just focus on the temperature, so we have the sun, which is around somewhere around 6,000 kelvins, that actually emits in the visible band primarily. Like the peak radiation occurs in the visible band. So that is why we can see the things that we can see in our world, in our real life, in the visible bands, because our eyes are also adjusted to that to see the visible band. On the other hand, if you lower the temperature, the peak wavelength actually moves further. So for example, Earth, which is at a much lower temperature as compared to the sun, that emits somewhere in around 10 microns is the peak temperature, right? So this is where it comes that, okay, all the earthly materials and the surface of the Earth that emits in this wavelength band, which is actually the thermal infrared, right? So that's how this principle of thermal infrared remote sensing works, because most of the Earth's surface peaks in radiation at this wavelength, and that is where if we design our sensors to detect this particular band, we can sense, okay, how much thermal infrared radiation it is emitting. All right, so. So what happens when a ray of light interacts with the terrain surface, right? So suppose you have a patch of land, and there is this incoming ray of light, right? And so three things can occur to it. Either that particular patch of land will reflect all of the radiation, or it will transmit all of it. Suppose it is a transparent material, it will just transmit all of it, or it can actually absorb all of it, or any of these can occur in fractions, right? So a part of it could be reflected, and part of it could be absorbed, and part could be transmitted. But the overall fraction is always one, which that means is just like reflected by incoming. So if we just take the fractions of all of them, that amount to one. Now, so this law that I showed, the Planck's law, it was actually derived for a specific kind of body which absorbs all the light that is radiated on it, right? So if there's incoming light of say 100 units, it will absorb all the 100 units, right? So that particular body is actually called black body. So here, the alpha, which is the absorbed radiation, that is always one, right? So whatever you put on it, it absorbs all of it. That's why it is called black, because nothing comes out of it. Epsilon, you see, I will explain it later, but it is called emissivity. So this is a law. The amount of radiation that anybody absorbs, the same amount of radiation it always emits, right? It's like how much you put inside that body, that it will throw out the same amount. There's no change in it. So for black body, because it absorbs all of it, it emits all of it. However, in our real life, not all the materials, or actually black body doesn't exist, like ideal black body, there is no such thing. So in the real body, for that, while the absorbed and emitted are always same, but they are always less than one, because a part of it is reflected, a part of it is transmitted, right? So that is where this concept of emissivity comes, which is very important when we will deal with how to get the water temperature. Is that so emissivity is defined like how much. So if you have a real body, and it is emitting, say, 100 units of radiation. And now if there, instead of that real body, if it would have been a black body, how much radiation it would have emitted, right? So if you take the ratio of that, that is called emissivity. So for a perfect black body, emissivity is 1, but for the other bodies, it decreases. So just an example of how of the typical values of the, water surfaces. For example, we have tap water, we have distilled water. So depending on the properties of water, the emissivity changes. And this emissivity also changes with the wavelength. So if you are looking at the thermal infrared region, so like most of the materials have this emissivity of more than 0.8. So they emit very nicely in thermal infrared region. And that is also one factor why thermal infrared is possible, because most of the objects emit a lot in this particular wavelength band, right? So these are just some examples of how the emissivity varies. You can see, like for water, it is almost varying in 0.95 or to 1, and that is very good, right? So we can sense the water from thermal infrared. All right. So if you look at it at a typical satellite thermal sensor, right? If you have a thermal sensor hovering around us, what it will measure? So we have a number of sources of radiation, right? So these purple dashed lines, they just show the radiation from different sources. For example, sun is emitting something and it gets reflected from the water surface. That is also coming to the sensor. We have reflections from tree, we have reflections from cloud, scattered radiation from sky and all of that, right? So we have multiple sources of radiation. But the thermal sensor will only sense the radiation that is coming in the thermal infrared band. That is the reason it is called thermal sensor, right? So so this orange arrow that shows here, this is actually what is sensed by thermal sensor, which is the thermal infrared radiation in the thermal in that band. So so this is like a variable called spectral radiance. Sounds complicated, but it's very simple. That amount of radiation that any patch of surface emits in a particular wavelength and per unit area of that surface, right? So if you take a unit 1 meter square surface of that particular body, so how much radiation it will emit in a particular wavelength, that's what it is. And that's what its Planck's law is, that I just showed a while ago. And so because this law was developed for a black body, which is a perfect emitter, and which we do not encounter in real life. So I'll come to that later. But so how do suppose I know how much radiation was sensed by this thermal sensor. So can I back calculate and get the temperature, right? It is possible, right? So this is one of the ways we derive the temperature from the output of this thermal sensor. So if we do a back calculation and invert this relation in terms of temperature, we get this equation, right? It's a simple equation. This is like a inverse log. And so now we get a value of temperature. Suppose it was 100 units of radiation, and if we invert it, we got, like, say 20 degrees Celsius. Now this 20 degrees Celsius is obtained by assuming that the body is black body, which is not the real case, right? So we need to make some adjustments and get the actual temperature of the body. So this temperature, which is by assuming that the body is black body, it is called brightness temperature of the body. And so to get the actual kinetic temperature, we need to make some adjustments based on the emissivity, right? So that's where emissivity comes into play. And so because if you see, this kinetic is the one that is measured if you stick a thermometer in the water. But that is not the case in case of remote sensing. So that's why we do some measurements. And so just an observation here, because emissivity is always less than 1. So we have brightness temperature, which is always lower than the temperature of when you stick it to a thermometer. All right. So now coming to the satellites that we have right now and how we can do using the available satellites. So we have Landsat 7. So Landsat 7 actually, it has 2 bands in thermal infrared, band 6 with 2 different kind of radiometric resolution. One of them is higher, other is lower. It depends which one you use. Usually we use the higher one, but then depending on the applications, you can use either of them. And the spatial resolution is 60 meters. If you remember, or if you have used it before, you might know that the other bands, for example, visible or near infrared, they are all at 30 meters. But because of the limitations of the sensor, as the wavelength gets higher, it cannot sense the surface at the same resolution. So the resolution has to go higher because we are going at a higher wavelength. So this is one of the limitations, that we cannot go at 30 meters. Then we have Landsat 8, and here actually the spatial resolution got even worse and it became 100 meters. And we have band 10 and band 11 in case you want to use it. Again, we have these two thermal infrared bands. And when the Landsat like disseminates the product, they resample it to 30 meters, just so that we have a uniformity in the pixel size. But then you should know that the original resolution is 100 meters and 60 meters for these applications. Now, coming to the important part. So now we say that, okay, the thermal sensor is measuring the radiation, and then we can say, okay, it is from the water surface. So we invert the relation and we get the temperature. But meanwhile, coming from the surface, like we have the surface here, all the way to the sensor, there are some changes taking place, right? Yeah. So there are some changes that takes place from to that particular radiation when it comes from the surface all the way to the sensor. What happens here? Well, actually, if you like try to divide how much. Suppose the satellite sensed 100 units of radiation, that thermal sensor. Now, from these 100 units, actually a major part of that radiation is actually contributed by sources that are along the way, right? For example, it gets scattered along the way, it gets interrupted by the clouds, haze, we have smoke, right? Like we had, yeah. So, and then the viewing geometry of the sensor. So multiple factors actually they actually change the radiation that was emitted from the surface. So we need to correct for that, right? Because we were assuming before, in the illustration I showed in the previous slide, that all the radiation that is emitted by the water surface is captured by the thermal sensor, and then we inverted the relation. But then there are some changes to that. So how do we do that? So there's multiple algorithms to correct for that. Essentially, for correction, what we do, we add some correction terms to the radiation that is sensed by the thermal sensor here, right? So we need to correct for all these particular sources: scattering, emission, absorption by the clouds, and correct for the geometry and all, right? So there are multiple algorithms. One of the algorithm I have also shared this paper on the drive, which actually using this single channel algorithm. So what it does is, because we are not aware of, we don't have the information about individual sources, so it actually tries to approximate some of these contributions using the atmospheric water vapor content. So water vapor can approximate kind of how much is the water vapor, how much is the amount of interruption of this or of this radiation coming back to the sensor, right? So it uses that to correct for that. So if you are interested, you can read more about it.
Shahryar.
Yes.
Can I just ask you, there is a question from Awad Muhammad Ali. Sure. I'm just asking a question because it might be related to next slides. So I was asking in slide, I think 14, if you go back. Yeah. I think Awad, you can also unmute yourself. He was asking about the spectral radiance in methods, what the variables stands for. Maybe slide 13.
Okay, sure.
Yeah, here. I think he's asking about the different variables maybe in these equations.
Sure.
Awad, please correct me if I'm wrong. I mean, you can unmute yourself and
yes, right.
Sure. Thanks for the question. Yeah. So as I mentioned, so W is the amount of radiation. Just assume it to be amount of radiation that is sensed by the sensor. Now, coming to this equation, we have lambda, that is the wavelength of the radiation that it is sensing, because every sensor is designed for a particular wavelength, right, to sense. For example, thermal sensor is designed for a certain band of radiation that it can sense only. So that is the wavelength lambda, and then T is the temperature of the surface emitting, and then C1 and C2 are constants. So if you look at the expanded form of Planck's law, there are like multiple variables, but then all of it are combined in C1 and C2 as two constants, right? And so the units of this will be watts, which is the amount of energy that it is getting, or power, for example, watts per micrometers, which is the wavelength per lambda, and per unit surface area per meter square, right? So if you see the units, it should be something like that. and then, yeah, I don't see any other variable here that I mentioned. So in very simple forms, there are only two factors that define this radiation. One is the lambda, the wavelength in which we are sensing, and the temperature of the body. Is that clear?
Yeah, I think so.
Yes, thank you so much. Okay,
Sure.
bye.
Yeah.
Thanks, Shahryar. I'm sorry for interrupting you.
Sure. Yeah, thanks. All right. So coming to this part, does it always work? Right now we had a theory, but then in practicality there are some changes. Right, there are some limitations that we should be aware of. So, for example, here's an example showing an example of a reservoir, and then this is a dam here, and this is a river, right? So you can see in the winters, like for example in January, there are some snowy conditions here, and actually the whole lake has a layer of ice sheet on top of it. And now, if you know, the temperature that will be reflected from this ice will be obviously somewhere, it will be negative, right? And it will be less than 0. So that is what the satellite will sense. But then the water below it will have some different temperature, and that is what we were interested in before, right? Not the ice temperature, right? So this is what we should be aware of as we go into the winters, and if there are some snowy conditions, the temperature will be affected, and it will be something else, not of the water beneath. And actually, if you know that the temperature of the water is what is affecting the organisms living there, not the snowy, the ice. Another factor. So what if you have a very narrow river channel, right? So for example, I show here like it's a part of a river below one of the dams, and so you see it's very, very narrow. You see the scale is 20 meters here, and so 20 meters is like I think the channel is around 15 meters or so at the narrowest point. So, but then you know now that the Landsat 8, for example, here is at a original resolution of 100 meters, right? So these are the resampled pixels at 30 meters. Even those are larger than the river width, right? So now what happens if we have a pixel that covers both land and water? So now if you have a pixel that covers both of them, the emission that will be sensed by the sensor, that has contributions from the surrounding environment, land, for example, trees, and also from the water, right? So that gets corrupted, right? You cannot say that only the water was contributing to that emission, but also the trees and the land other part. So now you see, if you see this part, actually this is the same portion. We cannot see actually where is this river, right? Because now all the radiation that is sensed is actually kind of mixed of land and water, so you cannot really identify the river temperature. So this is another limitations, that whenever whenever you pick a river for remote sensing or any application, so that should be at least if you are using Landsat 8, it should be at least 100 meters, right? So that you can get pure water pixels. All right, so this is a summary of what I described until now. So starting from the Landsat 7, suppose you have for some application, how do you get to the surface water temperature? So you do multiple things. You get the top of atmosphere reflectance, which is nothing but what the sensor sensed. Then you apply this atmospheric correction to go all the way to the surface. Then to correct for those different factors like smoke or haze or cloud and all of that. Then you have the radiation at surface. You correct for the emissivity because it is not a black body. So you get the corrected surface radiance for the real body. And then you invert the Planck's law. And so that you can get the temperature of the body. So that is kind of, it will be, so now after correcting all of it, then you can say, okay, this is somewhat close to what a thermometer will measure. But I still mind that the temperature is still for the surface, not for the whole body, because only the surface is contributing. Around top 100 micron of water surface is contributing to the emission. And then you can do some classification. For example, you can use any WI that you have used in exercise. Here I'm showing is like another method called dynamic surface water extent. And there are multiple methods of water classification because you only want the radiation from water, not the land. So you do that, and then you can average temperature over the water pixels only. And finally, you can get the surface water. So this is, I guess this is more described in detail in one of these papers I have uploaded on the drive as well. All right, so let's look quickly on the example. Let me take the time. Okay. So what happens when we have a dam? So if you have a dam, it actually tries to, it stratifies the pool behind that. What I mean by that is the top surface will be in contact with the air here, right? So that will be warmer. But as you go down, the temperature, the sunlight doesn't penetrate that much, and then you have a cooler temperature here. So that's what I show here in this plot. And so usually when the reservoir is operated, for example, hydropower or water supply, they tend to release from the bottom portion, right, to use the whole head. And so that obviously will be releasing from this pool, and that is cooler than what we found originally, right? So that is one of the limitations, or not limitations, but one of the characteristics of reservoir. So a quick example of Detroit Dam. So it is one of the dams here in the US. And so you can see here, it's a picture of the dam. So we have penstocks at the very, very bottom of this reservoir. Penstock is nothing but suppose the tube from which the water flows downstream. And then, so if you look at the profile of temperature, now you see that, so the red dots actually show the upstream temperature, the reservoir temperature, right? And the downstream, the downstream river, that is shown by this blue curve. Now you can see there's a change in how the profile looks like, right? So during the summers, the peak temperature actually shifts from suppose it was peaking in July at the upstream part, but now it is peaking at the downstream part in September or something, right? So many agencies actually define this as a biological criteria for what the temperature should be. So for example, for Detroit Dam, you can see they have defined this dashed line. It should not exceed that much. The downstream temperature should not exceed that much, depending on what kind of fisheries live there, right? So we have some fisheries that require at least this amount of, not more than this temperature to spawn properly or to reproduce properly, right? So you can see that this portion is this red signal that we are exceeding that foundation. So this is what we need to be aware of, and this is how the dams can affect. I will show quickly, I might be running short of time, but I will show very quickly another example of, so now we know that the existing dams are actually changing a lot, this river temperatures. So can we use, yes.
I think you're okay with time because we started a little like 10 minutes late, so
okay, sure.
No problem.
Okay, yeah. So now that we know the existing dams actually alter the temperature a lot, and we have seen an example of Detroit Dam. So let's see if you can use remote sensing and other techniques as well to predict how the future dams will be changing, right? So this is just one quick example. This is data set I think Hisham also showed yesterday, which actually says that how much, where and how many dams are planned in for future. So there are some dams that are under construction, there are some in plan, and you can see most of them are like in these mountainous regions, for example, Himalayan region and this region, many of them. For Egypt, for example, there's GERD, and then there are multiple dams. Hisham was showing a study for the Nile Basin, right? So you have all of these dams planned. And interestingly, you will see that for the developed nations, such as in US and Western Europe, there is no dam plan, right? Because we already built so many dams in the last century, so we don't have any dams here. So this is really critical for our developing nations where we are building more and more dams, and we need to be aware of that. Where will be these located? A study shows that majority of these future dams actually will be built in the regions where we have very high share of threatened species. So they measure the species, for example, different mammals or different fisheries. So they measure on a level of I think low to high, how threatened are they in terms of the population, right? And when they overlapped this data set of planned dams with the threat of the species, they actually found an interesting result that most of the dams are planned in basins that have threatened species a lot, that have a large number of threatened species. So this actually creates a signal or warning that we are building in the regions that are actually affecting the species a lot, right? So we need to look into how much actually these future dams will be affecting those species as well. So this is the research question. So how can we predict this thermal impact of future dams? Obviously, we cannot just predict in the future. So for that, we are using the existing dams as a guide to learn from the patterns. So we proposed a framework called Futurist, Future Temperatures Using River History. And what I mean by that is, the idea here is to first use a set of existing dams. For example, US has a big set of existing dams now that it has built over the past century. So first derive the thermal impacts. By thermal impacts, I mean how much change is from the upstream to downstream. So do that for the existing dams, learn from them, and develop some relationship with the dam characteristics and climate and all. Once we have learned it, then we can go ahead and validate in some of the locations in the developing nations and see, are we predicting good enough or no? And then finally, we predict the impact of future dams. So this is kind of a frame overflow of how we are doing. And so this number shows the number of dams we picked in this particular study. For example, we picked 107 dams in the US to study these thermal impacts, and then validate over 27 dams, and then globally we predicted for the future dams. And I should mention here, these dams are hydropower dams, and specifically those for which the purpose is for hydropower of water supply, because those are the dams that tend to release from downstream. So to get the thermal impact of existing dams, we need to know what is happening on ground, right? So for example, one way is to use in situ temperature gauges, thermometers, upstream and downstream, right? So we can do that for a dam. Here is a dam, and this is a reservoir and a river flowing down. But then we cannot do for all the dams, because in situ networks is still limited, right? So that's when the remote sensing can help us. Now, as I mentioned, one of the limitations was it cannot detect narrow channels. So what we can do is we can predict only the reservoir, which is much more wider than the downstream part from the remote sensing, and the other part from the in situ. So these are the two options we can use. So using this particular framework, we selected 107 dams in the US to study these existing dams, the thermal impacts. And here I show this. So I used Landsat 7 because it gave a long period of time for the thermal for the temperature records, and then I compared with the in situ temperature as well. So to see how it performs, right? So you can see most of the times it predicts the temperature very well. There are missing points in the winters, because that was one of the limitations, because for some lakes it becomes snowy, and so the temperatures are negative, so we have to remove that. And then for some dams, other dams, it predicts quite well. The bias is quite low. All right, so now we know we have the remote sensing temperature, as well as for all these existing dams, the temperature change between upstream and downstream. So let's see how has it been over the past few years, right? So over the period of record, I guess multiple dams have multiple period of records. Some of them have 10 years, 15 years data. Some of them have one or two years data. So using that particular data, all of this is in situ and remote sensing based, and all of these are existing dams. So we see here, I show here this thermal change, which is actually which dams are cooling and which dams are warming. So there are some dams, and this I should mention here, this is for the summer season. So in the peak season of suppose June to August. So now we see here some dams are actually cooling a lot in the summers, and very few dams are there that are warming. So if you focus on specific dams, like I'm showing like 8 dams here. So you can see here how it varies, right? That's quite interesting, because we have downstream temperature profile, right, downstream of a dam, and the red one is the upstream thermal profile. You can see there's a lot of variation, like multiple different dams behave differently. We have some dams that totally suppress the peak of the temperature, right? It's a constant temperature. And some of them actually are quite close to the upstream, some of them are warming. So we see here 2 dams that were warming. So we can see that, okay, these are warming here, this is warming, right? Downstream is higher than. So now, we want to learn from these dams, right? So for that, I'll not go into details into this. We use a database approach of artificial neural network. So it is a machine learning technique. Some of you might be aware of it. So it can learn from the different predictors you give, and then it can predict something, right? So here we are giving multiple like inputs. For example, dam heights, how is the reservoir, bathymetry, climate, and season, obviously season, and then the climate class and all of it. So we input all of these parameters into this model, and then try to predict how much will be the temperature change upstream from downstream. All right, so once we do that, we also validate it in the developed Southeast Asia. As I mentioned, over 27 dams. I'm not showing it here. Now, once I learned and then validated the model, we then go to the global dams that are planned for the future, and specifically hydropower, right? So here's a set of 217 dams, or 216 dams, I guess, overall over the entire world. And now we see how the temperatures will be likely to be in the future for a particular summer, right? So this is not like any particular year. This is like over a period of time. How will the changes be, right? So we can see some interesting patterns. For example, I'll mention GERD here. So this one is the Grand Ethiopian Renaissance Dam. That you can see it is going to be cooling a lot, right? And the markers are, the points are sized by the storage. So you can see many of the dams that are severely cooling are actually having higher storage, which makes sense because as the reservoirs get deep, they stratify more and they tend to cool more, right? So, but then there are few dams here in Western Africa where they are warming. And why are they warming? Because obviously some of these dams actually, they are very, very shallow. So that means that stratification is smaller and they tend to be warming the downstream part. So this is like kind of a picture of how we can see that these dams will be changing the temperatures for those particular rivers. If we scale this to these individual basins, we can also see some interesting information. For example, there are some basins that will be cooled, and there are some basins that will be there are some basins warmed and some basins cooled, right? And just to mention, I forgot to mention here, when we say severe cooling or moderate cooling, so we define some thresholds, and for that actually, so these thresholds are kind of flexible. So if there's any particular specific application, we can change these thresholds, and then depending on also on the kind of fisheries. For example, suppose some basin has particular kind of species that are very, very sensitive, right? So the definition of severe to moderate will change accordingly, and the model results can change as well. So this is kind of flexible in that. So this is what how we can predict the impact of the future dams. So just some key takeaways from this study and from the overall area of remote sensing of river temperature. So remote sensing can actually help us drive the water temperatures, and for applications in sustainable river management, right? Because we have built so many dams, and so we have changed our natural environment so much, but we have not really taken into account how much it affects the environment, right? So, and then to take into account, we don't have the data, right? If we start with in a basin that has no gauges, how are we going to monitor that, right? So that's where remote sensing helps a lot. And then there's a small observation here that, okay, the reservoirs that will be kind of deeper and stratify more, and then they tend to release from the bottom pool, they will be cooling a lot in the downstream rivers. So this observation is quite useful in terms of, for example, future dam planners. Suppose they want to plan the dam at a particular site. Now they can look into the ecology of that region and what kind of aquatic habitat is there. And so based on that, they can accordingly design their dams. So we should not have that deep, that suppose if there is a very sensitive fish species that is sensitive to temperature fluctuations, so they should be designing a reservoir that is kind of small, I can say, right? It does not stratify a lot, and so that the temperature effect is minimal. So this is one of the impacts that this study can have. And then finally, we do need to understand these future thermal impacts to meet these demands, and then while also ensuring the safety for the biodiversity, right? So we should be not compromising with the safety of ecology to meet energy and water needs. Yeah, I think that's it from this talk, and I'll be happy to take questions.
Thanks very much, Shahryar. That's a very comprehensive presentation. Yeah, I really like it, and it's very interesting to see how the temperature for the future hydropower dams, especially here for the GERD, for example, that's very interesting. So, yeah, let's take questions. So I see Awad is raising his hand. So go ahead, Awad, unmute yourself and ask a question.
Okay, thank you so much for your informative presentation. Can you go back maybe 3 or 4 slides?
Sure.
When at that slide, when you are showing the different dams with different back. Okay, yes. So no, after that.
Oh yeah, sure. This one?
No, after that.
Oh,
after this also. Yes, this.
Okay.
Okay, so your justification for these dams for being severe warming, you say that because they are shallow. Maybe at that period from between June and August, maybe they as you see, maybe Ethiopia, the, the maybe along the year, the temperature maybe does not exceed maybe 25% or maybe 30%. Okay, so I think maybe it depends on the temperature at the place itself and the season, not also the depth of the reservoir.
Right, right. Yeah, yeah. Actually, you're right. So there are multiple factors to that. And so as I mentioned here, so there are like, so all of these factors go into the model. And then, so it's kind of, it learned from what it happened in the past over the existing dams from all these factors. And then it is saying in the future, with that kind of environment and that kind of temperatures, that will happen. So obviously, yeah, stratification is one of the factors, but then we have climate and we have elevation and we have ambient air temperature. So you're right, yeah. So all these factors are actually contributing to that. Yeah, you're absolutely right. Also, also you can see that because northern hemisphere is warmer in June to August as compared to the southern hemisphere. So, so that is also one of the factors that might be changing here, because there are some dams that should have warmed if we use this. I mean, if they were in the northern hemisphere, but then because the temperatures were changing, so that actually is taken into account here as well. Thanks for the question. Did I answer your question?
Thank you.
Yeah.
Thanks, Shahryar. Yeah. Thanks very much, Shahryar. Yeah, we have one more question from Targan. Yeah, so it's Targan's raising his hand. Unmute yourself and ask a question, Targan. Targan is from Ethiopia, so he should give us like more insights into the GERD. So let's see. Okay, Targan, go ahead.
Okay, thank you for your holistic research presentation. What I have a question for you is regarding the title you raised for your research paper. Can you consider that this satellite-based research, that means thermal impact on research, remote sensing consideration, we can consider for future it can impact on, for example, I am from Ethiopia. What is its impact for the GERD? For example, for the decision makers, there is a conflict between the upstream or the downstream or the middle-rich countries. That means the riparian countries are in conflict in the current situation. Is that possible to forward depending on the research, depending on this area what you raised, can we say, or can we do research on this area for the decision makers which may lead for agreement of the riparian countries?
Yeah, that's a very good point, because yeah, as Hisham was also showing yesterday, that for the transboundary basins, so we don't usually have data from the upstream countries or downstream countries, right? So
Sure.
in terms of yeah, stakeholder engagement, it's very important to use like sources like remote sensing, because that information is obviously is public to anyone and anybody should be able to use it. It's free for everyone, right? So yeah, it's a very, very important thing that using this remote sensing, because we, like in our group, we do like a lot of this transboundary research. Hisham has shown, Nishan is doing, the previous speaker as well. So we have been doing this transboundary research, and then obviously remote sensing is a very, very important part of it, because even if you go into other conflicting basins, for example, Mekong, so there are data issues because sometimes the upstream country is not sharing the data with the downstream countries. So yeah, I mean, for stakeholder engagement and for reaching an agreement, if you have, if you can say, okay, you are using remote sensing for using the water information or information on these kind of impacts, for example, how much temperature will be changing. So I guess, yeah, remote sensing plays a very important role. And yeah, it's definitely a study, a domain of study, future study. Yeah.
Thanks, Targan. Yeah, that's, I think, a very important point, especially regarding using science to resolve some of these conflicts in the transboundary basins. So yeah, thanks very much. I hope we do something for the Nile River in the future, so we can use remote sensing to resolve all of these conflicts that's going on. Thanks very much, Shahryar. Yeah, it's a very important question. I think maybe we can take just one more question. We have, or maybe two. We have one from Muhammad Abdul Awal, yeah, from the Water Board, I think, in Bangladesh. So he's asking, Shahryar, the model was developed from US data, but predicting global dams. Do the prediction represent for countries other than US? Thanks.
Thanks.
Yeah. I think this question we discussed yesterday. Okay.
Yeah, yeah, actually, yeah, that's a key point and should be taken into consideration. So we did take into consideration because, so we tried to, the model we developed from US dams, so we tried to first validate them over existing dams in developing nations as well. So for example, I just put a slide in the appendix here. So we try to validate, for example, in the Mekong Basin. So there are some dams in the Mekong Basin. Those are existing in the basin, right? So we tried to predict them, and we were able to say by around 80% these thermal change classes are predicted accurately. And if you consider just the changes, warming versus cooling, if we ignore the moderate and severe, that actually accuracy goes to 95%. So we did actually try to validate. We also validated in part of it in India. I'm not showing it here, but then yeah, we try to take into like the best we can do using the existing dams. Because actually, if you see, my plan was actually to validate over multiple dams all over the world. But then the problem is like we didn't have the in-situ data, and even for remote sensing, we have to kind of validate it with the in-situ data. So we did that here because we found that data from some agencies, but then it was kind of hard to get data for other countries in the developing nations for validating. So we did what we can for validating it, and then we tried to predict for the dams, the future dams.
Thanks very much.
Thank you, Shahryar.
Yeah.
Thanks, Mohammed, for your question. So let's take the last question from Mohammed Alimain. So unmute yourself, Mohammed, and go ahead. Yeah, thank you.
Okay, thank you, Shahryar, for the presentation. I have a question. Did you consider global warming impacts in these thermal changes?
Yeah. Thanks for asking that. Yeah, I did consider. Yeah. So another part of this study was to consider different scenarios of increase of temperature. For example, there are some scenarios that say there will be increase by 2 degrees Celsius by 2100. There are some scenarios that say 6 degrees Celsius. So because our model was actually using the ambient air temperature here as one of the inputs, so we directly just changed these input air temperatures and tried to see how is the impact changing. And so I didn't show the result here, but then we found that the basins that are warming will be warming even more, obviously, because air temperature is there. But the basins that are cooling, or the dams that are cooling, they will minimize in their effect of cooling, because the effect is kind of nullified because of the cooling and the air temperature getting warmed. So yeah, but the effect was smaller. It's not. I can say sometimes it is not very significant, because the increase in temperature is like around 1 or 2 degrees Celsius also. So the model is not very sensitive to that. But then for some dams that are very, very big, the changes are actually visible. Yeah.
Okay, thank you.
Thanks. Yeah.
Thanks, Mohammed, for your question. Thanks, Shahryar, for your great presentation. Yeah, that's wonderful. I hope everyone learned from this presentation, and I think we will stop here for the break. So probably we will reconvene back at 9. We should be back at 9:15, but let's say let's be back at 9:20. So we will start the next presentation at 9:20. Thanks very much. I think, Shahryar, there is a question. You can answer this question on the chat box, maybe for everyone, if you don't mind. Muhammad Ahmad is asking, is your model will be applicable to every place in the world?
Sure, I can answer here. Yeah.
I mean, you can. Yeah. You wanna? It's okay. I mean, if you wanna answer it, it's okay. If you wanna answer in the chat box, it's fine. Whatever you prefer. I mean, because maybe some people maybe they are in the break, so they might.
Oh, okay.
See the answer maybe later when they come in the. You can do both of them. I mean, you can answer it here and then write it in the chat box as well. So yeah.
Yeah. So it's kind of like it is supposed to be applicable every place in the world, because it's kind of using, because actually US is a good test bed, because it has all kind of bathymetries, all kinds of climate and you can see like how it varies and how wide is the US climate, right? And then we have different terrain elevations, different climate classes. So we picked US for that reason only, and then we have a lot of existing dams as well, so that it could be representative of different climates in the world, right? And then we tried to validate as well in the developing nations for some of the dams that were available to us. So it is supposed to be applicable every place in the world, but obviously, any model is not perfect. So yeah, we might have inconsistencies, or if there is a very extreme climate, or if the dam size is such that the model has never seen before, right? So those cases might be challenging to model. Like for example, if you try to model in the Arctic, what will happen, right? So those cases might be challenging, but then at a very big scale, we can say that model is designed to be applicable in challenging climates, in different climates.
Thanks, Shahryar. Yeah, thank you very much. Yeah,
Thanks.
I hope this answers your question, Muhammad. And if you can type it, Shahryar, that would be helpful as well. Thanks.
Yeah, I'll type.